I'd like to welcome you all again to NSERC Permafrost Net's seminar series. And today's presenter is Lucas. He's a first-year master's student at the University of Calgary under the supervision of Dr. Brian Moorman. With a background in physical geography and a fascination with the potential of machine learning techniques, Lucas is determined to involve the predictive capabilities of machine learning with the study of Arctic ground ice or snow. He had the opportunity to go to Svalbard in February of this year, where he collected snow depth and density data for his thesis. With any luck, we'll hear all about it in this presentation. Whenever you're ready, Lucas.
All right. Thank you for the introduction, of course, and thank you everybody for being here. I do just want to preface this presentation before I get going by reiterating that I am indeed a first-year master's student, and as such, I don't have any research of my own to share yet. I recently defended my proposal. So I have a research plan, and my research plan did include this method I'm going to share with you. But this presentation will more so be an outline of the foundations and the methods for applying a terrain-based approach to snow depth prediction, as opposed to what I have learned myself by applying it. So it'll be a little bit different from what we've seen previously, but it should be fine, I think. So my agenda is fairly straightforward. As I said, I don't have any of my own results or work really to provide. So it'll be pretty introductory heavy in terms of the insulative properties of snow, its relationship with permafrost, and why snow depth is being singled out here, as opposed to some of the other potential metrics. I'll then discuss my study area in Svalbard a bit and why it's a good candidate for such a model. I'll go over the method, the outputs from previous studies, as well as the uses for such a model. So the thermal conductivity of snow, as we should all know, is what is responsible for its insulative properties. It is usually represented or gotten by measuring density as a function of density. But in reality, the density simply serves as an easier to measure proxy for the snow microstructure. And this snow microstructure is what is truly responsible for the thermal conductivity. The density provides like a crude measurement as to the packing of the snow grains, and consequently how much air is present in the snow. And this enables its use to determine the thermal conductivity. The amount of air present in the snow is relevant. We can see in this figure on the left. It's relating the thermal conductivity to temperature. We can disregard that temperature for now. So I simply just want to draw your attention to the orders of magnitude difference in the thermal conductivity between ice and air. So as we have a low density snow with a lot of air in it, there's a, for lack of a better term, a less robust ice skeleton to conduct this heat. And so naturally, the thermal conductivity in this graph is low. But as that density increases and we sort of crush out those air pockets and shrink them down, the ice skeleton gets more robust and we get a higher thermal conductivity as density increases. Important to note, though, is that this relationship obviously is not linear. And there's a lot of scatter between the measured data here and the effective thermal conductivity. They're using effective thermal conductivity here as they're only considering conduction and not, say, convection as well for methods of heat conductance. So this variability in the measured densities and thermal conductivities is not due to measurement error in this. It's simply because you can have multiple different thermal conductivities at a specific density, because the density is not the underlying phenomena that controls thermal conductivity. It is the temperature of the snow, it is the size of the grains, and it is the bonding of those grains. So it's complicated when you want to model the effects of snow on the ground thermal regime, because density is not a perfect metric. So the idea of this presentation and this method in general is to find perhaps an alternative that is easier to perform with less data that might get us there. So this snow microstructure, as I've said, is really the underlying controlling factor for thermal conductivity. We can see here in this figure on the left, different snow types and their relationship with density and thermal conductivity. It's much the same as the previous figure in that there's quite a lot of scatter. And essentially, the different snow types here are resulting in different levels of bonding. This alters the density in a complicated way, but also the ability of the grains to conduct heat, which is what we really care about. But to add even more confusion, the density and the thermal conductivity here are not always related. So in this figure on the right here, there's these two top plots. where small rounded grains and recent snow are examples. This dotted line is the linear fit to the data. These solid lines are the quadratic fit. We can see that they agree. They're moving in the same direction. So the authors of this paper, Sturm et al., have concluded that you could use density to get an understanding of thermal conductivity here. That's not the case with these two types of snow, depth 4 and mixed forms. Mixed forms being a more metamorphosed type of snow, where the linear fit and the quadratic fit tend to cross each other. So as I mentioned, density is a poor metric for trying to understand thermal conductivity of snow. Microstructure is better, but even when you understand, if you think that you could get density, for example, and sort of derive microstructure from it, that's not the case. So what this all suggests is that if you want to model the effects of snow on the ground surface or permafrost temperatures, it's complicated and it requires an understanding of the snow microstructure. But unfortunately, it's extremely data intensive to get data about the snow microstructure, especially if you're looking to categorize or quantify the influence of the snowpack over a large area, for example, in my study area. So before I continue, it's important to understand why the relationship between snow and permafrost is important. I mentioned previously that there's a relationship. Snow can insulate the ground, but it can also serve to cool the ground surface. So this figure on the right here is from a paper published in Svalbard last year. Initially, what they were trying to do was investigate the influence of snow on vegetation. And to do that, they erected this snow fence that we can see in the 2017 C here. Within 10 years of putting up that fence, enough snow had accumulated in the lee of the fence to warm the permafrost and collapse the ice wedges that were present there. And this formed these really deep gullies that we can see filled with water. And what it suggests is that this deep snow accumulation can contribute to permafrost degradation, in addition to drastically altering the hydrologic drainage of the landscape. Conversely, in Antarctica, ephemeral snow has been shown to cool ground temperatures and reduce active layer thickness. And so there's a lot going on in this figure. I'll break it down here. So what I want to draw your attention to is this gray band. The data that they used was collected in 2018 and 2017. On January 13th and 14th in 2018, a snowstorm rolled in. It delivered snow depths of up to 38 centimeters. They covered the ground for 12 days. So that's what this gray band is denoting. There are two sites that we're considering here, this JGM site and the Calm site. And this JGM site was snow covered during that period, and the Calm site was adjacent to it and not snow covered. And what we can see is that the active layer thickness of that snow covered site goes to 0. The active layer completely refreezes due to this snow depth, whereas the adjacent uncovered site, the active layer thickness reduces, but it does not refreeze. And moreover, this subsurface temperature at the snow-covered site was 5 degrees colder than the snow-free site. So quite a substantial influence of snow on the active layer in this case. There is more. So again, a complicated figure. There's really 4 subplots here. Each one of these subplots is a transect in the snow-covered site, the JGM site, where they used GPR and manual probing to get not only the snow profiles that we can see at the top here, but also the thaw depths. This top plot is January, the bottom is February. These lighter colors are 2017 and the darker are 2018. So I'll remind you that the snow that we're discussing here dropped in January of 2018. And relative to the previous year that did not see this snow, we can see that the thaw depths are significantly reduced. Right? It's a little less clear in these bottom 2 plots. Obviously, there is some difference, but a lot of that is owing to this inconsistent snow cover that we see here as opposed to the top 2 plots. And even a month after that snow disappeared, we can see that the thaw depths in 2018 are still reduced compared to the year previous. So the significance of this is that direct connections are being made between snow depth and active layer thickness, or more broadly, the ground thermal regime. And that is sort of why snow depth is being focused on here. I mentioned it's difficult to get data on snow microstructure. That is less so the case with snow depth, which I will describe shortly, but a little taster is that it can be collected relatively simply in terms of manual collection, but also with remote sensing. which is something, as far as I'm aware, is not possible with snow microstructure. So if we're able to connect these measurements of snow depth to perhaps thermistor measurements or borehole measurements, we could empirically relate snow depth to its effect on the ground thermal regime and go from there. So snow-covered conditions, as I mentioned, this is sort of more of a recap, are considered the most critical factors in determining heat flux to the ground and also controlling ground temperatures in permafrost terrain. And different depths of snow have been associated with differences in air and ground temperature. So this figure that's been lurking here is from Chen and colleagues in 2021. They did a surface energy balance for this road, this subarctic road environment, where the road was plowed, but these embankment slopes were not plowed. And what they determined on those embankment slopes was that as the snow depth was increasing, the difference in temperature between the top of the snow, or the air effectively, and the ground surface also increased exponentially. And the heat flux through the snow, as that snow depth increased, reduced exponentially, right? So again, there is the idea is that we can take these snow depth measurements, or in this case, a high accuracy model over a large area, and relate these predictions to thermistor measurements or borehole measurements to establish relationships between snow depth and the ground thermal regime. My study area is in Svalbard, you can see here. My study area is Scott Turnerbreen forefield, the same as Liam Carson, who we heard from last week. It's about 15 kilometers southeast of Longyearbyen, the main city in Svalbard. Latitudinally speaking, it's at about 78 degrees, so it's snow covered for much of the year. So this is a high resolution DEM of my study area. It's at about 8 centimeter resolution. And just from glancing at it, we can tell topographically that there's a lot here. This is a deeply incised river fed from a glacier down south, this back of the glacier, I should say, or back of the DEM. The side walls of the study area are steep. There's boulders here, and owing to its recent deglaciation, there's no vegetation here. So this makes this study area in particular appealing to apply a terrain-based method for snow redistribution, as there's no confounding effects of vegetation here. There is one more thing to consider, and that is that there have been recent developments of retrogressive thaw slumps in the study area, which again are the focus of Liam Carson's research, which we heard about last week. But what this means for me is that this study area, it confirms it's underlain with permafrost, and that permafrost is responding to climate change. So given all that I've just discussed about the insulative nature of snow and how it has some effect on the ground thermal regime, this study area is covered with snow for much of the year, and likely is having an influence on how this permafrost is responding to climate change. But in order to quantify that, the end goal, we first need to be able to model this snow, right? It's unreasonable to expect that we would take enough samples distributed across this study area that we could simply linearly interpolate it. So that's what this model is focused on, is modeling snow depth. Okay. So the method itself, it appears rather straightforward. And compared to physics-based models, it is. So there's a lot to consider when you want to model snow depth. Obviously, precipitation and temperature are important factors in the initial snow input. But once the snow is on the ground, topography, wind, and vegetation largely control how that snow is redistributed. And the relative importance of each of these factors on the redistribution of snow really depends on where that study site is and what kind of landscape it is. So is it a mountainous area, or perhaps a tundra, a deep valley, a prairie? Some might have vegetation, some might not, for example, with my study area. And then once redistributed, elements like incoming radiation and snow microstructure are responsible for describing how that snow cover evolves. So the best way to model this, I don't think this is a controversial thing to say, would be to include all of these factors. And you can do that with physics-based models, but they are extremely data intensive in that firstly, you need to be measuring all of these different factors, and then you need a model large enough to utilize them all. And that's simply not possible in my study area, and certainly for a lot of other study areas around. So a simpler method that has been applied recently is using machine learning to produce high accuracy snow depth maps in mountainous and Arctic terrain. And these previous studies have found that the topographic position index and the upwind slope index were most critical for model predictions. These elements can be extracted from a DEM, save for wind direction. Obviously, the upwind slope index requires a wind direction. You can get that from a weather station or a global wind product. So combining these metrics, the topographic position index, the upwind slope index, and your snow depth points into a random forest algorithm, this algorithm can learn associations between them and make predictions across the entire study area, which I will describe a bit more in depth shortly. There is a little bit of a caveat or something worth mentioning here, and that is while this method is less data intensive than a physics-based model would be, the drawbacks of using a machine learning algorithm here is that it requires a significant number of snow depth points. You can see that asterisk down on the thousands of snow depth points. This is the reason why I'm unable to use this in the study area currently. When I was up in February, I was unable to collect enough snow depth points to train the model robustly. So that's a little bit of a downer. The upside is that manually collected snow points and also remote sensing techniques for collecting snow points via terrestrial laser scanners have both been used to produce high accuracy results. So while there's a bit of a data bottleneck here, you need to spend a lot of time collecting snow depth points. In theory, you could use a remote sensing method and get just as good results. Obviously, this random forest algorithm is producing these snow depth maps. So what I'll do is go over the topographic position index and the upwind slope index and describe them, how the random forest algorithm takes this all into account, and then go over some previous examples of models or previous examples that have successfully employed this method. So the topographic position index is a measure of relative elevation. It is important in defining ridges and valleys for snow redistribution, particularly in flat areas. It is a pixel-based index that compares the elevation of every pixel in the raster to the average elevation of its surrounding pixels via a user-specified radius. So in this diagram I've created on the right here, we imagine this blue pixel as our pixel of interest, and there's this radius of pixels around it. The difference in their elevation is obviously assigned as the index, and the sign and the magnitude of that index are relevant here. So a positive index indicates a ridge or a topographic high. A negative index indicates a valley or a topographic low. And that magnitude communicates how pronounced that ridge is or how deep that valley is, which is necessary in this context for determining if a cell will experience erosion by wind and lower snow depths or snow accumulation and higher snow depths in a valley, for example. What you will notice is that this index is a difference, obviously, and one of those values in the difference is an average of the cells around it. If you change the size of this radius, so too will the index, which will change how the model perceives that cell value, right? So this user-specified radius is an inherently scale-dependent phenomena. It should rely on the scale of processes you're looking at. In this context, I mean, are you considering the microtopography of your study area more or the macrotopography? If you're looking at, say, meter or 5 meter intervals and how microtopography will influence snow redistribution and snow depth, you might choose a smaller radius versus if you're looking at a very large, say, 1,500 square kilometer study area, you might be more interested in valleys. You could look at hundreds of meters of a radius instead, right? It should also, in this case, as I just mentioned, rely on your study area size and to a lesser extent, the computational power of the machine that you're using. The more cells that you include in this radius, the more computations or calculations are required and the longer it can take to process. So it's a bit of a balancing act here as well. This sort of idea of using topographic position index stems from sort of this poster presentation by Weiss, where they have used topographic position index to classify slopes, so upper slopes, lower slopes, cliff faces, and it's dependent both upon the sign and the magnitude of the index. The same idea is applied here or is adopted here, where the TPI value is characterizing cells in the raster in terms of susceptibility to accumulate or erode snow. The upwind slope index is similar. It's a method for identifying sheltered and exposed cells and accounting for wind redistribution in steep areas. It is different in that it relies on the mean wind direction recorded for that period of interest to identify cells that shelter or expose areas downwind. And what do I mean by that? So a vector emanating from the cell of interest is pointed in the mean wind direction. The length of this vector is a user-specified variable. It's much like the radius for TPI is scale dependent and should depend on the same factors: the scale of processes you're looking at, your study area size, and to a lesser extent, your computational power, to name a few. So the slope between the cell of interest and every cell intersected by this vector is calculated according to this equation on the bottom. This figure on the right, we can see we have a cell of interest and we have a vector emanating from it. It is intersecting all of the cells along its length, and it's calculating this equation. We can see that in this bar plot here. Ignore the numbers and the letters. This is taken from the original paper that introduced this method. The idea is that here is the cell of interest, and the maximum slope difference identifies the shelter defining cell. In this case, for 1, it's A, and that difference in slope is assigned as the index to this cell. Same thing here with 3 and B. The difference in slope is assigned as the index. And much like with TPI, the positive and negative values, or the sign, matters, as does the magnitude. So a positive index indicates that the cell is sheltered. We would expect that with 1 here. Remember, the wind is coming this direction. So it's coming over this ridge. This is sheltered by A. So we would expect more snow accumulation in a sheltered area, right? A negative value indicates an exposed cell. So for 3, it's on a ridge relative to B, right? So we would expect a lower snow accumulation due to wind erosion, right? And then the magnitude communicates how much, or perhaps the influence of topography on that cell with respect to it. So there is one more thing to mention here, and that is that the mean wind direction is an interesting metric, to say the least. Obviously, the wind blows in different directions, and even beyond that, topography or vegetation in a study area would deflect the wind, right? So to account for this, what is done is an arbitrary window is placed around these vectors, here of 60 degrees, and you use multiple vectors to gather data from more cells. Each of these vectors would have its own index, its own maximum difference in slope, and the average is then assigned to the cell of interest. Okay, so we have topographic position index, we have our upwind slope index, we have our snow. Now, naturally, you would include other variables. Slope and aspect are common. Vegetation indices are also common if your study area is very heavily vegetated. These would all form your training data set. So these are all in a raster format. You know where your snow depth points are, you extract the relevant cells, and this forms a training data set. Typically, it's about 70 to 75% of your overall data, and the remaining 30 or 25% is left to validate the model after. So a random forest algorithm is a type of machine learning algorithm. It generates multiple decision trees using randomly sampled points. And often you will hear the term bagging associated with random forests. This refers to bootstrap aggregating. It's the method for data point selection and algorithm prediction. From the training set of data, points are randomly sampled with replacement. So this means that each of these trees is produced with a completely random subset of data. And this is the bootstrapping portion of bagging. It helps to reduce variance in the data set and also inject randomness into the trees. Once these points are selected, each tree is learned on the data, the subsample that it has, and the algorithm selects the optimal splitting point on its way to making a decision. So there are splits occurring at each of these nodes, right? The difference with random forests is that the number of features considered at each split is restricted to a random subsample of all of the possible features. This ensures that the correlation between each of these trees is weak and that the resultant prediction of each of these individual trees is robust. And so what I mean by features, in this context, we have TPI, we have SX, we might have slope, we might have aspect or vegetation index. All of those are potential splitting features. As opposed to looking at all of them, this model may look at, say, slope and TPI, and this one may look at aspect and slope, for example, each one being different. And that ensures that each tree is looking at the maximal amount of data that it can. So each tree will end up making a unique prediction down at the bottom here. And in this case, as it's a regression exercise, we're predicting the centimeter value of snow depth for a particular pixel. The model's overall prediction will be an average of all of the tree's predicted values. So this is the aggregation portion of bagging. There are a few user-specified parameters here, mainly indicating or dictating how many trees you use, how deep these trees go. In this case, they go 3 deep, right? They could go deeper, and how many features should be considered at each of these node splits. But the majority of the work is being done by the model itself. Okay, so what has previously been done? This is a paper published in 2022 by Malosh and colleagues. They used this method to produce this snow depth raster in the west of Nunavut. It was quite a large study area, about 1,500 square kilometers. So this is their raster that they produced. This is their input parameters in raster format. Notice SX and TPI. They used these vegetation indices and determined that they really did not improve the model accuracy all that much, which is why this presentation only touches on SX and TPI as they've been deemed the most critical. But of course, you'd be using more than simply SX and TPI when you're doing this on your own. They produced a root mean square error of 8 centimeters on their map, so rather high accuracy. A similar study, Revuelto and colleagues in 2020. This was not done in an Arctic setting. It was done in a mountain setting in Europe. They had 3 different study areas, and they used the terrestrial laser scanner that I mentioned earlier to collect their snow depths. This is a map of those snow depths, and this is the rainforest output, these being the errors associated between the prediction and the observed values. So depending on their study area, as they had 3, their errors were on the order of millimeters to centimeters. So again, quite high accuracy. And really the beauty of this methodology comes down to its simplicity and the fact that it can be completed with remotely sensed or manual data and analyzed entirely in programming languages like R and Python. So this suggests that the processing and analysis to produce an estimated snow depth map can be completely automated and updated by feeding in new DEMs to extract new predictor variables, new wind data, and new snow data. So this methodology is flexible in that it can produce maps for a discrete time period or daily or monthly or annual estimates should your data collection methods allow for you to get that data. So I've discussed previously how I believe this could be used in the context of permafrost, but it's important to note that it's also been used for snow water equivalence. So snow depth has been shown to be more spatially variable than snow density in previous works. Obviously, snow depth is half of what is required to get snow water equivalence. And so as it's been shown to be more spatially variable, it is seen as the driver behind the spatial variability of snow water equivalence. So this method was used to get higher accuracy cell or pixel predictions for snow depth, and then multiplied these values by some basin average density in order to get higher accuracy maps of snow water equivalence. So useful for a few different study angles, I should say. Yeah, that is, pardon me, all I have. I know this presentation was a little different than we've seen in the past, so I just want to thank you all for taking the time to listen to me and for putting this forum together.
Thank you very much, Lucas. Now I'd like to open the floor to questions. Does anyone have a question? I can go first. I was just wondering if you considered other types of machine learning algorithms besides the random forest and why you chose that, what some pros and cons might be.
It's popular in the literature for a few reasons. One being it's more interpretable. That's sort of why I favor it. I think the decision tree aspect of it makes it more interpretable than, say, a neural network, which is more mathematically based and difficult for me to understand, which is why I'm doing a poor job explaining it. But in terms of computational efficiency, it balances predictive accuracy and data requirements quite well. So that's sort of why the literature has and why I have. Other studies have used other methods, some boosting methods, if you're familiar with those, or other machine learning methods have been used. They obviously have their strengths as well. But this random forest method seems to be a nice balance and easily interpretable.
Very nice, thank you. Any other questions? NJ says, do you consider vegetation?
I'm actually no longer using this method in my own study area. which is unfortunate. But that was one of the factors about my study area that was important, is that there's actually no vegetation whatsoever. So if I were to apply this in my own study area, I wouldn't. Obviously, I just presented one of the studies that has used vegetation, so it has been done, and there are different ways to do that, but no, I would not be.
I'd like to thank you again, Lucas, for the presentation. Wishing you the best of luck in the rest of your masters. Have a good day, everyone.
Thank you all.